So last time you took notes, you actually only took notes on the rules and the easy examples. So today we're going to work on the challenge examples. Now these are more like the ones that you'll actually see on tests and quizzes and on the STAR test and in higher level classes, because we really want to challenge you guys to know these exponent properties and use them properly. So a couple things we need to talk about before we hop into these rules. The very first thing I want you to know is that dealing with coefficients, or the regular numbers, you're going to act just like you always have. So we're going to remember to treat numbers like we've always treated numbers. Okay, we're going to treat numbers like normal. So if we are multiplying terms together, we're going to multiply the big numbers. Now we add the small numbers because remember there are different rules for exponents than there are for regular numbers. For example, in this first little part right here, I'm going to zoom in so I can highlight better. But in this first example, you have some coefficients. Then you have some A letters. Then you have some B letters. We have to do each part of these with the bases that match. So the rules for regular numbers are the same. I'm just going to multiply the regular numbers. -2 times 7 is -14. But when I get to doing the A's, I have to remember that when I multiply bases, all I do is add those exponents together. And when I get to the B's, I have to remember that there's invisible ones right here. So when I multiply those bases together, I'm just going to add the exponents. -14a to the 5th power times b to the 2nd power is the correct simplification of this problem. If we look at the second challenge example here, again, notice that we have coefficients and we have R letters. We have to treat each separately according to their rules. So coefficients or regular numbers, you treat like regular numbers. If we're multiplying these things together, we're going to do 12 times 2, which is 24. And then when we multiply the R values together, this is going to be R to the 12th times R to the -10th. So I add those things together. 12 plus -10 is 2. 24R squared is the simplification of that expression. So the rules stay the same for big numbers, and they do the exponent rules for the exponents. Let's move on to the quotient rule. The quotient rule is when we're doing division. Hopefully you remember that when we divide, we actually just subtract the exponents. But again, if you have constants, if you have good old-fashioned numbers, you're going to treat them like good old-fashioned numbers. In this problem, we have constants, we have x's, and we have y's. We're going to do them each separately. So take the constants and follow constants rules. Good old-fashioned division. 27 divided by 9 is 3. Then we switch to the exponent rules when we have exponents. So the x bases, we're going to subtract 5 minus 2. We're going to get x to the 3rd power. For y to the 4th divided by y cubed, we're going to get y to the 4 minus 3, which is y to the 1st power. Or just simply y if you don't want to write the hidden 1. I want you to pause the video and try this next one. I think you guys can do the quotient rule for the next challenge example. Hopefully when you pause the video and tried this, you ended up with 9h squared j by taking the constants and actually dividing them, but then subtracting the exponents. Notice how j doesn't have anything to subtract with it, and that's cool. It's just going to hang out at the end of this term since it didn't get reduced at all. Cool. Let's go to the power of a power rule. This is the one that, I'm doing air quotes again and you can't see me, looks like distribution, but it is not distribution. Before we get started on any problem that has a power rule, I recommend going through and writing in the invisible exponents. The invisible exponent on this 5 is a 1. We can see the exponent attached to the x, but we can't see the exponent attached to the y, so we're going to write in the number 1. I recommend doing that because when you draw your not actually distribution arrows, so that we remember we're multiplying exponents to exponents, kind of like distribution, again, it's not distribution, we'll know we do this right. Okay, we have to do each property. So we'll have a constant, we'll have some x's, we'll have some y's, and we'll have some z's. Every single one of them gets distributed, again, air quotes distribution, by that 5 that's on the outside. We're going to give exponents some exponents. So here we go. This is going to be 5 raised to the 5th power, 1 times 5. It's going to be x raised to the 10th power, 2 times 5. It's going to be y raised to the 5th power, 1 times 5. And it's going to be z raised to the 15th power, 3 times 5. Now that's an acceptable answer, but it's not actually simplified. If you guys remember back to when we did the very intro to exponents in class, we talked about how if we have just a regular good old-fashioned number raised to a power, when we simplify it, we actually need to do that multiplication. So what I would do before you finish this problem is check and make sure all of your constants are as simplified as possible. So instead of saying 5 to the 5th power, we're actually going to do that multiplication. 5 times 5 times 5 times 5 times 5, and get 3,125 x to the 10th, y to the 5th, z to the 15th. That is actually the simplified version for this problem. Cool beans, you are going to try this next one, but again, remember, before you get started on any problem that has powers raised to powers, I highly recommend showing all of the exponents that are hidden. There is a hidden exponent behind the 7. What is it? Yeah, that hidden exponent on any constant is a 1. So go ahead and pause this video and try using the power of a power rule for this problem. Sorry, I said pause the video and then I realized I had something I wanted to make sure you guys saw. Please notice that there are actually 2 power rules. You have this first set of parentheses and then you have a second set of parentheses. Each of them has its own power that it's being raised to. Okay, so whenever you go to do this, make sure your distribution, again, I'm using air quotes when I say distribution, has to be just to the parentheses that it's touching. So that 1/2 is going to distribute, air quotes, to just the 8, and this 2 is going to distribute to the 2 powers that are in its parentheses. Okay, now pause the video and try this one. Here's what I got, but I'm not finished. I just wanted to pause here for a moment because all I've done so far is raise the power to a power by multiplying each of the exponents by the number on the outside of the parentheses. 1 times 2 is 2, 3 times 2 is 6, and 8 times 1/2 is 4. Now I'm not finished because we do have a good old-fashioned number here. We can and we should multiply that 7 squared out and get 49, 7 times 7, and actually use that number as the coefficient of this term so that it is in its most simplified form. Now there's some really good pieces of information we need to write down on these notes when we get to our rational exponent property. This is the one where we have the acronym TIBO. TIBO still works. And you've probably thought about this whenever we did this lesson last time. You're like, Miss Quigley, when we learned about the symbol back in the day, we called it a square root. And now you're telling me it's called a radical. You are not incorrect. The shape itself is called a radical, and you've always called it a square root because typically we don't put a number right here. But since it's a square root, squared, all the squareds have 2. So there's actually an invisible 2 sitting right here. If that number wasn't written there, that 2 sitting on the outside of this little bitty radical, if it was just blank like this, we would still know that there's a 2 there because it is called a square root. This is the hidden math here. The invisible or the hidden root or radical is 2, which is pretty neat. So we want to be able to use the hidden math whenever we do it. If we take x to the 1/3 and rewrite it into radical form, let's go ahead and set ourselves up for success. We know there's going to be a radical and the base is x. Then we remember top goes in, bottom goes out. So that top number is going to go inside the parentheses and that bottom number is going to go outside the parentheses. Easy peasy. Now, because I did say I really want to make this as simplified as possible, we're going to go ahead and let this 1 be invisible. We know it's there because that's the hidden math, but that is much simpler to look at. The cube root or 3rd root of x. The last one, like I said, if you just see the root symbol or the radical symbol, you know that there's actually a 2 right there. So don't forget about that hidden math when we go and set up our base and a fraction to do top in, bottom out. Now wait a second, there's no top number, or there's no inside number to go on the top. What's the hidden math or the invisible number on the inside? Yeah, it's really an exponent, and the invisible exponent is 1, so there's a 1 on the top, and this invisible root that we now saw of 2. X to the 1/2 is just like saying the square root of x. Pretty cool. The last two problems, again, these are the easier, in my opinion, rules. Some things I want to make sure you understand about the negative exponent rule is the only term or part that moves in a term is the negative exponent. Okay, only the term or the part of this term that has a negative exponent attached to it or leaning on it is the one that moves. So if you look in this first example, you see how up here, this x squared, it's already positive? He's happy, leave him there. But this guy's sad. So we need to hammer time him to the opposite side so that he becomes happy. Since he's already in the denominator, we don't put denominators in denominators. That's not really a thing. So instead of moving it from the numerator to the denominator, we're just going to move it from the denominator to the numerator. Since there's nothing in the denominator, it's really got a 1 down there. And we can simplify this down to just x squared y to the 3rd power. Remember, if the term is positive, if the part of that term has a positive exponent, you leave it where it is. Don't move it unless the actual thing that the exponent is touching is negative. Cool. Look at the next example. There are actually 3 pieces here. We have a constant, we have some z's, and we have some x's. Only 2 of those 3 parts of this term have a negative exponent. Because remember, this 2 really has an exponent of positive 1 attached to it. So we shouldn't move the 2 when we take care of our negative exponent rule. But we should make sure we move the denominator x negative 2 up to the numerator and say x to the 2nd power. And we should take the z to the negative 5th power that's in the numerator and hammer time it down to the denominator so that it's positive. Only the negative exponent moves. Only the negative exponent moves. And last but not least, our favorite / most simple exponent rule is the 0 exponent property. Now we said 4 to the 0 power is 1 and that 98 billion number to the 0 power is 1. Notice that only the term with a 0 exponent is equal to 1. That means that in this top expression, it says 1 plus negative 30 to the 0 power. Well, negative 30 to the 0 power, that's going to be 1. But I still have 1 plus that now 1. So don't just automatically think that because you see a 0 exponent that the whole thing is 1. Remember, only the term with the 0 exponent attached to it is 1. Which means if we look at the bottom example, it says 50x plus 300y to the 0 power minus 25. The whole thing is not equal to 1. But this first term right here, all of that is equal to 1. So really, this expression is just like saying 1 minus 25. And 1 minus 25 very easily is negative 24. So we're going to take the very simple or basic exponent rules that we learned about in the last couple classes, and we're going to make them a little bit more challenging. But fear not, you guys know the rules, and if we treat numbers like normal, we'll be absolutely fine. See y'all in class.